Ever feel like, you're kind of stuck, like you're wrestling with this mountain of data and you're just trying to build a model that just, makes sense. And not only makes sense, but it's accurate too.
Yeah, finding that balance can be tricky.
It really can. So that's why we're doing a deep dive today into this technique called, it's called the lasso.
And it's really cool. It's like this secret weapon for building these smarter regression models.
It is. Think of it as a way to cut through all the noise in your data.
Yeah. It helps you zero in on the variables that actually matter, the ones
Yeah.
that are really driving the outcomes that, you actually care about.
Exactly. And what's really cool is that we're basing this whole deep dive on a research paper. Get this. It's called Regression Shrinkage and Selection via the Lasso. Now, I know what you might be thinking. Shrinkage sounds a little scary, maybe a little technical.
Right. Don't worry, we're going to unpack all of that.
We are. But before we get into the nitty-gritty, let's talk about why the lasso is even necessary. I mean, we already have things like ordinary least squares regression, right?
Right, those traditional methods. But, as you've probably experienced, those methods, they have their drawbacks.
They do.
Subset selection, for example. You can be really unstable.
Oh, yeah. Like trying to build a house on a foundation of sand. Not very reliable.
Exactly. And then there's ridge regression, which can be the opposite problem. It's like this black box where you get the results, but you don't really know what's going on under the hood.
Right. You're kind of just left wondering, how did it get those predictions?
Exactly. That's where the lasso comes in. Think of the lasso as this balance beam. It's trying to find this sweet spot between minimizing those pesky prediction errors. We're always battling those, but it does it with this really clever constraint.
Okay, so it's like walking a tightrope between accuracy and what was the other thing?
Interpretability. We
Yeah.
want a model that we can actually understand. And the way the lasso does this is by keeping the sum of the absolute values of those coefficients, those numbers, that tell us how much each variable impacts the outcome. It keeps those below a certain limit.
Okay, I'm not gonna lie, that sounds a little technical. Can you break it down for us a little bit? Like, what would be a real world example of this?
Sure. Imagine you're working with a budget,
Mm.
right? You've got a certain amount of money, and you want to make the most of it.
Who doesn't?
Right. The lasso is kind of like that. It's figuring out which variables are the essential ones, the ones that give us the most bang for our buck, and which ones we can maybe do without.
Oh, okay. So it's like prioritizing. We're giving more weight to the variables that really matter and kind of pushing the others to the side.
You got it. And the really cool thing is this budget that we're talking about, it's actually a parameter that we can control. We call it the tuning parameter.
So it's like adjusting the tightness of the lasso, right?
Exactly. And the tighter we make it, the more those coefficients get shrunk down. Some of them even go all the way to zero.
Wait a minute. So you're telling me that some variables might actually get completely eliminated from the model?
Precisely. And that's the beauty of it. By shrinking some of those coefficients to zero, the lasso is basically doing variable selection for us. It's highlighting the most influential predictors and saying, hey, these are the ones you really need to pay attention to.
That is really helpful, especially when you're dealing with like tons of potential variables. It's like the lasso it's like a magnet, just pulling out the important stuff.
It is. And what's really cool? They actually have a visual representation of this in the research paper.
Oh, I love visuals.
Yeah. Figure 2, it compares the lasso to ridge regression
When?
using these really cool geometric shapes. And you can actually see how this plays out.
I love when complex ideas have these like visual counterparts.
Absolutely. It's like it just makes it click, right? And what's really neat about the lasso's geometry is that it forces some of those coefficients to get trapped at zero. And this makes a huge difference because the model becomes so much easier to wrap your head around.
Oh, okay. So it's not just about getting a model that's more accurate. It's about getting a model that we can actually interpret and understand.
Exactly. We want to be able to tell a story with our data. And speaking of stories, let's look at a concrete example from the paper. They actually use this lasso technique on a data set about prostate cancer.
So they were using the lasso with this prostate cancer data, trying to predict, what was it, levels of a certain antigen.
Exactly. Prostate-specific antigen, or PSA. And yeah, they wanted to see if the lasso could identify the key factors that influence those levels.
And could it? Did it manage to pinpoint anything useful?
It did. It actually zeroed in on 3 main predictors: the volume of the cancer, the weight of the prostate, and then whether or not the seminal vesicle was invaded.
Interesting. Were those surprising at all?
Well, here's the kicker. Those were the same predictors that were identified by traditional subset selection.
Wow. So it's like the lasso, it's almost like it found a shortcut, right? Like it arrived at those same insights, but with this added bonus of shrinking those coefficients, giving us a clearer picture of what's really going on.
Exactly, that's a great way to put it. You see, traditional subset selection, it can be a bit, well, it can be a bit dramatic.
Yeah.
It tends to exaggerate the importance of the variables that it keeps, making them seem more important than they might actually be.
Oh, I see. So it's kind of inflating their impact.
Exactly. The lasso, on the other hand, it's more, shall we say, level-headed. It shrinks those coefficients, giving us a more realistic, more accurate sense of how much each variable is truly contributing.
Okay, that makes sense. But I'm curious, how do we actually find that like perfect amount of shrinkage? It seems like a delicate balance.
It is. It's like tuning an instrument, right? Too tight, and you're going to break a string. Too loose, and it sounds terrible. Finding that optimal tightness for the lasso, it's crucial.
So how do we do it? How do we find that sweet spot?
Well, the paper talks about three main methods: cross-validation, generalized cross-validation, and then there's Stein's unbiased risk estimate.
Okay, those are some pretty dense terms.
They are, aren't they?
Can we like unpack them a bit? Like let's start with cross-validation. What's the gist there?
Sure. So with cross-validation, the whole idea is to make sure your model isn't just good at, fitting the data you use to train it. We want to make sure it can generalize, that it can perform well on new, unseen data.
Right, because what good is a model if it can't handle anything new? It's like if you only ever practice playing the piano in your living room and then you went on stage and totally froze, that wouldn't be good.
Exactly. You need to be prepared for the real world. So with cross-validation, you're essentially giving your model a bunch of practice runs. Imagine you split your data into, say, 10 groups.
Okay, 10 groups. Got it.
You train your model on 9 of those groups, and then you test it on the remaining group. And you repeat this process 10 times, each time leaving out a different group for testing.
So it's like giving your model a chance to like try out different combinations of the data and see how it does.
Exactly. By doing this multiple times, you get a much better sense of how well your model is going to perform when it encounters brand new data.
Okay, that makes a lot of sense. So what about those other two methods you mentioned? Generalized cross-validation and Stein's method? Those sound even more intense.
They do. But they're really just different ways of trying to find that optimal tuning parameter. Generalized cross-validation, it tries to be a bit more computationally efficient, which I know is something you appreciate.
Efficiency is key.
Right. And then Stein's method, it has its own advantages in certain situations, especially when you're dealing with a lot of predictors.
So it's like having different tools in your toolbox. You wouldn't use a hammer to tighten a screw, right? You pick the tool that's best suited for the job.
Precisely. Now, I don't want to get too sidetracked here, but there's this fascinating connection to Bayesian statistics that I think you'll find really interesting.
Oh, I love when different areas of statistics like intersect. It's like these hidden pathways, you
And
know.
it's like discovering a secret passage.
Yeah.
So the lasso, believe it or not, can actually be interpreted from a Bayesian perspective.
Okay. I'm intrigued. Tell me more.
It implicitly assumes something called a double exponential prior distribution for those coefficients we've been talking about.
A double exponential prior. That sounds a little intimidating.
It's not as scary as it sounds. Think of a bell curve, right? That's your typical normal distribution.
Yeah, I've seen those.
A double exponential distribution is like a bell curve, but with a much sharper peak and heavier tails. And this shape is really important because it reflects the lasso's tendency to favor coefficients that are either pretty large or exactly zero.
So it's like the lasso is saying, I'm betting these coefficients are either going to be really important or not important at all.
Exactly. It's making a statement about which variables it thinks are going to be the key players, even before it's seen the data. And this is actually quite different from ridge regression, which uses a normal prior, that smoother bell curve we talked about. And this difference, it's subtle, but it's a big reason why the lasso is so good at picking out those really impactful predictors. But here's the thing, and this is what makes the lasso so powerful. It's not limited to just simple linear regression.
Wait, really? We can take this lasso beyond straight lines. Tell me more.
We can. Remember those generalized linear models we talked about earlier? The lasso can be applied to those too.
Right, like when we're not just dealing with a yes or no, but maybe a range of outcomes, right?
Exactly. Things that can't be captured by a simple straight line. And the paper actually gives a really cool example using a data set on kyphosis,
Kyphosis, that rings a bell. That's
the curvature of the spine.
right, right. Of course.
And they use the lasso to figure out which factors are most predictive of this condition. And it just goes to show you how versatile this technique can be.
So we've got linear regression covered. We've got logistic regression covered. What about other types of models? Does the lasso, does its reach extend even further?
It does. The paper even touches on using the lasso with tree-based models.
Oh, right. Those are the ones that are kind of like flowcharts, right?
Exactly. They're great for making predictions based on these decision rules, but sometimes the way they're pruned back can be a bit, well, brutal.
Yeah, it's like hacking away at a tree with a machete. Not very subtle.
Right. The lasso offers a more elegant solution. Instead of just chopping off entire branches, it shrinks them.
So instead of a machete, we're using like pruning shears.
Exactly.
Much more precise. So this shrinking, this more nuanced approach, it leads to more accurate models.
It can. See, by shrinking instead of just chopping, we can end up with tree-based models that are not only more accurate, but also easier to understand. And the paper even talks about using the lasso with MARS.
Mars.
MARS. It stands for Multivariate Adaptive Regression Splines.
It sounds really complicated.
It does sound pretty intense, but it's actually a really cool technique for building these flexible models that can capture really complex relationships in your data.
Okay, so it's like fitting a curve to our data, but like on steroids.
Yeah, that's a good way to think about it. And the lasso comes in because it can help us make those Mars models even better
By shrinking things.
by shrinking things.
Mm-hmm.
It helps us figure out which parts of those splines are really important and which parts we can do without. So, we've been talking a lot about how the lasso works in practice, but this paper also dives into some of the theory behind it, like why it works so well. And there's this whole section on soft thresholding.
Soft thresholding. Now that sounds really complicated.
It's actually not as bad as it sounds. Imagine you're tuning a radio. There's all this static and noise, but you can kind of hear the faint signal of the station you want.
I've been there.
Right. So soft thresholding is like this process of filtering out the noise while preserving the important information, just like fine-tuning that radio dial.
Okay, I get the analogy, but how does this relate back to the lasso?
Well, in the context of the lasso, each of those coefficients we've been talking about, those numbers that tell us how much each variable is contributing, they could be thought of as signals.
Okay, let's call it.
And the lasso, with its unique approach to shrinking those coefficients, it acts like this soft threshold estimator. It's essentially identifying the true signals, the important predictors, by setting the noise, the unimportant stuff, to zero.
I see. So it's like the lasso is cleaning up the signal, making it easier to see what's really going on.
Exactly. And there's actually a theorem, backed by all sorts of fancy math, that shows that in certain situations, the lasso, through this whole soft thresholding thing, it actually performs incredibly close to an ideal subset selector.
Wow, so it's not just intuition here. There's like hard math backing this up. That's reassuring.
It is. And it speaks to this really beautiful aspect of statistics, this interplay between, our gut feelings about data, the real-world applications, and then these rigorous mathematical foundations. It all comes together.
It's like we're standing on the shoulders of giants, using these powerful tools to unlock the secrets hidden within data. So we've talked about how the lasso works, its connection to Bayesian statistics, how versatile it is. But what does all of this mean for someone listening who's, grappling with their own data out there in the wild?
That's the million-dollar question, right?
Yeah.
And the paper does a great job of laying out three main scenarios where the lasso really shines.
Oh, yeah, I remember this part. It was like they were categorizing the different types of data situations you might find yourself in.
Exactly. So, scenario number one. You've got a small number of really strong predictors. It's like trying to find a birthday present hidden in your living room. It's not going to be that difficult, right?
Right, it's pretty straightforward.
In this scenario, traditional methods like subset selection might be your best bet. The lasso can work too, but it might not be the absolute best tool for the job.
Right, because it's almost like overkill, right? If you don't need that much shrinkage.
Exactly. Now, scenario number two. This is where the lasso really shines. Imagine you've got a moderate number of predictors, and their effects are kind of moderate too. It's not immediately obvious which ones are the important ones. This is where the lasso's ability to both shrink and select those variables becomes really valuable.
It's like it's helping you cut through the clutter, zero in on what really matters.
Exactly. Now, scenario number three. Imagine you're drowning in data. You got tons and tons of predictors, but their individual effects are very subtle.
Oh, man, that sounds like a nightmare.
It can be. It's like trying to find a needle in a haystack.
Yeah.
In this scenario, ridge regression, which smooths out the effects of all those predictors, might be the way to go. But, and this is important, don't discount the lasso completely. Even when there are a lot of variables at play, the lasso can still be helpful in identifying the ones that have at least some impact.
So it's like even in that sea of data, it can still find a few glimmers of insight. So, like with most things in statistics, there's no one-size-fits-all answer. The best tool for the job depends on the specific data you're working with.
Exactly. And that's why it's so important to understand the strengths and limitations of each approach, which is, of course, what we've been talking about today.
It's been a great deep dive, and I feel like I've learned a ton, but I have a feeling that this is just scratching the
Oh,
surface.
absolutely. There's so much more to explore with the lasso. Like, how can we use it in even more complex scenarios? What about image analysis or signal processing?
Those are great questions. This paper has definitely opened my eyes to the possibilities. And on that note, I guess we'll leave our listeners with this. Given everything we've talked about today, its versatility, its ability to, cut through the noise and pinpoint those important variables,
Yeah.
could the lasso become a staple in your statistical toolbox?
I think it has the potential, definitely.
It's a powerful technique.
It is.
And I encourage everyone listening to, don't just take our word for it. Go out there, explore it, play around with it, see what kind of insights you can unlock from your own data.
That's the best way to learn.
It really is. Well, this has been a fascinating deep dive into the lasso.
I agree.
Thanks for joining us, and we'll see you next time.